Hello everyone. Um, just a minute. So yeah, we can start now. I'll be sharing my screen. Please let me know if you can see it. So I hope my screen is visible to everyone. I welcome you all to week 8 of our tutorial series on micro and nanofabrication. So today I thought first we will do a recap of all the lithography lectures that we have seen till now. Just because we have been learning this for a very long time, I thought it might be good if we can just do a small brief recap. So lithography is basically uh, transferring the patterns that we want, or the patterns on our mask, to the films or to our stack. So I can say it is transferring desired patterns to films. Sorry. Okay, so we have learned that we can classify the lithography techniques broadly in three categories. One is contact based lithography, so contact lithography. Another one is proximity litho, and the third one is projection lithography. So we learned these things in great detail, but to summarize in short, contact litho is basically when we have a mask. Say this is my mask, and I place the mask directly on top of my photoresist. So this is my substrate, or it can be any stack. On top of the substrate, I have spin coated my photoresist, and I place the mask directly on top of the photoresist. So there is a contact between the photoresist and the mask, and so there will be an illumination source. Right. So so that is what we do in contact lithography. So it will directly illuminate the mask, and basically we will be illuminating the regions that are open, and the rest of the regions will not be seeing the source light. And then based on whether our PR is negative photoresist or positive photoresist, we will be able to either preserve the photoresist in the exposed regions or remove the photoresist from the exposed regions. So similarly, in proximity lithography, everything else remains the same. There is a mask, there is a source. However, now what changes is, sorry, this is the source. Now we have a small gap between the PR and the substrate. Sorry, between the PR and the mask. So there is this substrate here. So now because of this gap, there will be some diffraction that is happening, and whatever is the image that is formed here due to this diffraction, that will result in the exposure of the PR. And the third one is projection lithography. Again the same concept. We have a source, but now the mask is placed after there is some lens. Then we have a mask here, some pattern. Then from the source the light will come it will diffract obviously. Then the lens will make sure that the pattern gets to the focused at the mask, and then again after light is coming to the mask, it will diffract again here, like from everywhere. So then this diffracted pattern will again be captured by another lens, and then that will be focused on our photoresist PR. So that is broadly the three techniques. So what are the let's look at briefly what are the advantages and disadvantages of these techniques. So first of all, let us look at the resolution. Typically in contact lithography, we get a resolution of 0.25 micrometers. So this is quite good resolution. Like if you compare it to proximity lithography, in proximity we have 1 to 2 micron resolutions. So in contact based lithography, since there is no diffraction that is happening, so the resolution is improved. Yeah, but still it is not as high as let's say projection lithography. In projection litho, we have resolution of the order of nanometers. So something like 20 nanometers is what we can achieve by using projection lithography. So the resolution here is this, and here it is this. So this is a we can achieve this if we use projection lithography along with immersion. So I'll say immersion based projection lithography. So immersion is basically so the resolution of the projection based lithography uh, is given by lambda over Na, right? Is directly proportional to lambda over Na, the resolution. So in immersion, what we do is we um, change the Na, numerical aperture of this projection lens, by uh, by immersing it in some higher refractive index material. So here earlier it was all air. Now we will put something like oil or some higher refractive index material, and because of that, this Na, which is nothing but n sin theta p, whereas this is the projection angle. So this n will go up, and because of that, this Na will go up, and because of that, lambda will Na will go down. So the smallest line that I can write, that is my resolution, the smallest line will be very small. So that means the resolution is better. So yeah, so that was about resolution. Um, so that is one of the advantages of using projection lithography, that we get very high resolutions. Another advantage of using projection litho is um, we get very good throughput. So in projection lithography, particularly in stepper we expose the entire mask at once, and the projection optics and all the optics is designed such that the entire mask receives uniform illumination, and because of the uniform illumination, the entire mask gets exposed at once, and there is no uh, mm, there is no error associated to the position variation. So uh, how to say this? So basically the optics is very sophisticated, and but that makes sure that the resolution that we get and the error rate that we get is very low. So yeah, now let us come to the drawbacks. So the drawbacks of contact lithography are that mask degrades fast. So naturally, since we are bringing the mask in contact with the photoresist, uh, it is going to collect some photoresist onto the mask, and how much ever we clean it, after some runs, after some lithography runs, it is going to get damaged. Mask degrades fast, and secondly, since the mask is again in contact with the photoresist, there is a chance that we transfer the some impurities from the mask onto the photoresist, creating a lot of defects. So the substrate will be defect, or the design that is transferred will be defect prone. Similarly, we have drawbacks even for proximity lithography. The most prominent drawback is that it is diffraction limited, so the resolution is diffraction limited. So in order to improve the resolution, we have to go to very low wavelengths, or or increase the numerical aperture, like in this case. And the drawback of projection lithography is just that it is very costly. Like, installation is very costly. Like, in the long run, if we are making multiple chips with the same mask, and or even with different masks, if we are if we are doing foundry level processing, then projection lithography is a more efficient approach, or more cost effective approach, but the initial installation cost of projection lithography is very high compared to the other two types of lithography. um, yeah So another advantage of projection lithography that we studied is we can do overlay with it. So overlay is basically when we have two different masks. Say one has a square, like we discussed this example in the last class, and the other one has a circle, and I want to write a pattern that is something like this. Then I will first expose using mask 1, then expose using mask 2 to get this. And this overlay is very critical to alignment. And this very fine alignment is actually possible in projection based lithography systems using something called as alignment marks. So on a wafer, when we are writing using a projection lithography system, we have multiple reticles, right? So each reticle we will expose with the mask, then move the wafer, and the next reticle again we will expose with the same mask, the next reticle with the same mask. So it might happen that the alignment might not be perfect for all the reticles. So first thing is we have global alignment marks that we put across the wafer. So so for doing different, so we are first writing the square layer, then writing the circle layer. So after writing this, first when we write the square layer, we align it to these marks. Then again when we are writing the circle layer, we again align it to these marks. And in addition, we can also have local alignment marks, so that every reticle gets aligned properly. So all that is possible in projection lithography, and it gives that is the reason it gives very good yield, or very good throughput. So there are two types of projection litho. One is stepper, and the other one is scanner. So they are just like the name suggests. So in stepper, we first have a mask, and we flood expose the mask, and there is some reduction in size due to all the projection optics in between, and on the wafer we will write that mask with the reduced size, say some 5x or 4x reduction in size will be there. So it will write one entire reticle at a time. So like I showed in the previous slide, right? No, here. It will write one entire reticle at the same time, and then the stage will move, and then it will write the next reticle. So we are not moving the mask, we will just move the stage in this case. So it will write one reticle, then step to the next. So that's why it's called stepper. Scanner, however, what it does is it moves both the mask and the both mask, or rather we should say slit, and stage. So there will be a mask, but we are not exposing the entire mask at once. We are exposing only through a small slit. So, say this is my mask with some patterns here. I will only expose a slit. So, I will have a slit opening and it will only expose some part of the mask at a time, and then this slit will scan across this mask. So, at a time I am not writing the entire reticle, however, I am writing a small slit of the and when the slit moves scans throughout the reticle, then the entire circuit is written. So, that is the idea of a scanner. So, you do not write the entire circuit at once, you illuminate it part by part. So, you would expect that the throughput is very high in stepper, and that is actually the case because we are able to write the entire mask in a go. However, we still prefer the scanners, and why is that? That is because better uniformity of illumination. So, it is very difficult to achieve the entire reticle that gets illuminated when we are illuminating it at once. It is good enough in case of stepper, however, for very critical devices it might not be that good. So, typically in IC fabrication technologies they prefer scanners because the entire slit will be illuminated uniformly and we can guarantee that, and because of that the scanner performs better than the stepper. Okay. So, after that we learned a few terms. Okay. Where am I? So, uh, so this we already know. Resolution is nothing. So, I'm just telling the formula. So, these will be helpful when we are doing problems. So, resolution of a projection based litho system is directly proportional to lambda over Na, and there is also some factor called K, which depends on other factors. So, yeah, so to enhance resolution, we basically have to uh, go to lower wavelengths or increase our numerical aperture or lower the K. So, the next term that we learnt is just a minute. Yeah, another term that we learnt is exposure latitude. So, this is basically the extent to which light sensitive material can be exposed, the exposure dose is there, right? The exposure dose can vary slightly. So, so with this variation, how much variation can we tolerate? So, I will just write the definition down so that it is clear. Extent to which light sensitive material so this term is also very common in photography, same concept applies there. So, yeah, extent to which light sensitive material can be exposed to still achieve acceptable results. So, so say my exposure, so say my line width can go, see, I expect some line width, but I can tolerate some -5 and +5% change in the line width. So, it can go a little thinner or a little wider. So, then my exposure latitude will be the exposure dose corresponding to the -5% line width minus exposure dose corresponding to +5% line width upon E naught into 100, because we write it as a percentage. So, the more my exposure dose, that means the more dose variation I can tolerate, right. So, more my exposure dose means the difference between the lowest dose that I can give and the highest dose I can give is more. So that means that I can tolerate more dose variation, and this more tolerance to more dose variation also translates to tolerance to more thickness variation. So it quantifies robustness of dose variation and thickness variation. So yeah, so we can easily calculate this exposure latitude by doing a simple dose test. We change the dose and see what is the change in the line width, and that can give us and that can give us the exposure latitude. So the next thing is depth of focus. Okay. So depth of focus, sorry. Right. So we know that the depth of focus is nothing but the distance between the two focal planes. So okay. So whenever we have a lens, it will focus at some point, right? Right. So this is my focal point, but based on the incident beam, the focal or based on the photoresist thickness that we are coating, the focal point might lie on just on top of the photoresist, or slightly inside the photoresist, or slightly here, like above the photoresist. So based on that, the image that the photoresist sees can be slightly thicker or thinner compared to, so the line width can be slightly thicker or thinner compared to the desired line width. So so the depth of focus basically tells us that how much of this variation that we can tolerate, and a simple relation for calculating the depth of focus was given in the class, and it is just lambda by 2 na square. Okay, or rather it's proportional to lambda by 2 na square we can say, but for all practical purposes we can use this relation. So another thing is that as we change the focal position, just like I said, we change in focal position, there will be a change in line width. So based on whether my resist is whether my mask is dark field, light field, it will either be a curve like this or a curve like this. So for now let me say that it's like this. So for the perfect focus, I'll get the correct line width, and if I'm slightly out of focus, I'll get the line width broader than what I expect. So okay. So this line width versus focal position also depends on the dose that we give. So just like I said here, the dose will change the line width, right? So say this is at some dose E1, at a different dose I'll get a different curve, and at a third dose I'll get a different curve. So so there will be some line width toleration that I can give. So say I am okay with having line widths between this and this, so then this is my so focal position between this, if I am giving E1 as my dose, then focal position between this and this is my depth of focus, and yeah, so this is my desired region. So for these focal positions and these energies, my line width is in tolerance. Okay. Okay, I'll just add another slide. Just a little more on the recap. Another parameter was linearity. So this is just simple. The PR dimension should scale linearly with the mass dimension. So the image that so the PR width that I get after development should be proportional to the linearly proportional to the mask width that I am giving. So otherwise the design that is transferred on from the mask to the photoresist will not be what we expect, right? Okay. So yeah, there was another class on mask making. So how do we make these masks? Or rather, more importantly, what kind of masks should we make? So the simplest type of mask is a binary mask. So binary mask is when we have quartz or a soda lime substrate. So based on the frequency range that we want to operate in, we will choose either quartz or soda lime as our substrate. So it should be transparent in those frequency ranges, source frequency ranges. And then there will be a chrome layer on top. So this is the opaque layer, chrome. Okay. And then we can also have a anti-reflection coating if we like, that will give a ERC. So that will that will give more clear image when we transfer the pattern from mask to the photoresist. So this is the basic binary mask. There is another type of mask that is commonly used, um, that is called the alternating phase shift mask. So in alternating phase shift mask, we have say this is my basic mask that I had, just a binary mask. But it might happen that if this is very small, then the diffraction pattern that I see here is something like this, and the pattern that I see here is something like this due to the other slit. So they might overlap with each other, and the final intensity that I see is something like this. So it doesn't drop all the way to 0 in the middle, because this is my electric field and this is my intensity profile. So what happens in an alternating phase shift mask is, I have a mask, but now since the top of the mask is glass, right? It's just soda lime glass or quartz or soda lime material, so transparent material basically. Uh, so now here what I will do is, I will etch some part of the glass as well, or some part of the other whatever transparent material we have as well. So because of that, there will be a phase shift introduced from the light coming from here and light coming from here, and then I make sure that this etching is so that the phase shift between these two is pi. So the electric field profile for the light coming from here will look something like, sorry, and for the light coming from here will look something like, it goes down. So because of the pi phase shift. So now what will happen is, it is going to 0 in the middle region. So the intensity, when we see, it will go to 0 in the middle region. So intensity is nothing but E square, right? So it will be like something like this. So that's the basic understanding of an alternating phase shift mask. Okay, so similar one more type of mask is there, that is called embedded phase shift mask. In this the principle remains the same. However, instead of etching the glass, what we do is we so this is the mask. Now I want to introduce a phase shift between this and this. I will just put a separate material here. Like the technicality of how they do it, how they fabricate such masks is very complicated. So the material in this slit will be different from the material in this slit. So that's why it's called embedded phase shift mask. Yeah. Okay. So other than that, one more last topic. It's of proximity correction. Was there any message? Okay, no. Yeah. So, uh, so on a mask we might expect a design. So we have some design like this, say, L-shaped design. Then when we do it on a, like when we project it onto our substrate, we might get some design with curved edges. So this is primarily because of some effect known as proximity effect, and this is very common, like so based on whatever is the pattern next to this, or it might happen that, so if you just look here, this corner light can come from here. See, this is the mask, it's opaque, say, and also from here. So at the corner the exposure is higher compared to say here the light can come only from this direction. So because of that there can be a edge rounding effect. Similarly here, and also because if sometimes we might have patterns very close to each other, and sometimes we might have a very standalone line. So the way the standalone line is transferred to the resist might be different from the way the closely spaced pattern is transferred, and that's also because of the same reason. Light passing will see more obstruction in this case compared to this case. So then what do we do about it? So there people have come up with very interesting strategies for this. They have so if this is my mask, this is the image that I get. So then they will say, if I want this image, what should be my mask? So then they will reverse engineer this mask. So it can be something like something which has broader corners, say. So they have different computational tools for doing it. So they will reverse engineer this mask, and this is the process called as optical proximity correction. So this is a step that comes just after the so after you get the design from the designer, what the mask fabrication team usually does is it will check for the design rule checks, and wherever it finds it is necessary to do this proximity correction, it will do the optical proximity correction. It is sometimes also called as inverse litho technology, because we are doing an inverse litho. So we want this image, so what should be my mask? So that's why it's sometimes also called as inverse litho technology. ILC, ILT. Okay. Uh, yeah, so that was about optical proximity correction. Sometimes they also use something known as sub-wavelength resolution assist features. So there will be some some very small features next to the design, or sometimes they will cut through the design with those very small features. And the idea is that these features cannot be resolved by the light anyways. However, they will just make sure that the so so here I said the light coming from all the sides to the corner, but it will just block some sides. So similar to this approach only, but in this we have to do a lot of computations to get to this, but this is just like an approximate way of predicting that this mask might give us a better image compared to the original mask, like that. Okay, so that was about mask making. Yeah. And so while yeah, we have talked mostly about I think most of the things now. Okay, so we can I think proceed to okay, one last thing I'll tell. So we have already talked about all these things. I'll just list out all of them. Resolution enhancement techniques. So first thing is obviously reducing lambda. Another thing is changing the source shape. So we will so by changing the source shape we can change the how the light diffracts and everything. And yeah, we'll do a problem on this, then it will be clear how this helps. Next one is we can do off axis illumination. So we didn't talk about this, but I'll just mention it here. So sometimes when we have very closely spaced patterns, the diffraction or all the diffraction orders might not be captured by the lens. So the first diffraction order might be captured. Sorry. So say the zeroth order is captured, but the first diffraction order is not captured. So without the first diffraction order, we can't do anything, right? So this is my lens. So then what they do is they instead of sending the light like this, they will send it obliquely, so at a some angle. So when we are sending at some angle, then the zeroth order will be here and we'll get first orders here. So we can capture both zero and first order. uh, my diagram is very poor, but just need to understand here that in case of off axis illumination, we are able to capture more diffraction orders because of the tilt in the illuminating axis. Then the next one is alternating phase shift mask. APSML, right? Another one is yeah, immersion litho, basically increasing the so having a higher refractive index material in at the projection stage. And another thing is double patterning, or this is something we discussed in last class, right? So all these things can be done to enhance the resolution. So okay, so now let us do some problems. So there are several steps involved in mask preparation. Arrange the steps given below in the correct order for an ideal mask preparation. So anyone wants to try this? So first, what would we do when we want to make a mask? What would be the first step?
Is it step 3?
Uh, Conversion of GDSI file to pattern generator compatible format. Uh,
Yes.
why do you think so? It is step 3. It was Vinay.
Because initially you need to develop a pattern to put it on the mask.
Yeah, yeah, exactly. So, so don't you think then the fourth step is the first one, right? So first we need to design the circuit pattern. Design the circuit pattern.
Okay.
Yeah, right. So yeah, you're right. So first will be the fourth step. After that, do you understand what I mean by this Boolean operation? So this is basically uh, based on the resist that I have. I either want to have a dark field mask or a light field mask, or so whatever editing in the mask that I need to do at the design stage itself. So like I might have a square, I want to write a square, but then I have a positive photoresist. So in the mask I should actually uh, okay, how to okay, I want to write a square pattern uh, and say I have a positive photoresist. So then in the mask I should illuminate uh, everything here but hide this, right? Sorry, say I have a negative photoresist. So if I have a negative photoresist, that means whatever is exposed, no, what am I talking? Okay, I'm confused right now. But whatever, we have some design, but we want to say um, take a knot of this design. So that is knot is a boolean operation. So I want to make my mask which looks something like this. So light is passing only through the center portion. Say I want to do that. So all those operations come just after the designing of the circuit pattern. So the next option is 1. Uh, okay, that's fine, right?
Yeah, yeah.
Yeah, okay, thanks. Then after that we will convert the GDSI. So till here it is still in the GDSI format. Now from this GDSI we will convert it to some pattern generator compatible format. So based on whatever tool we have, they have some compatible formats, and in that we will convert, and then we will send it for mask tape out. Okay. So 4132. Yeah. If the magnification factor of an optical lithography system is 5x, what is the dimension of the feature in the mask if the design feature width is 100 nanometer? So this is very trivial. We want a design feature of width 100 nanometer. So what should be the feature on my mask? They are telling that the magnification factor is 5x. So it should just be 500 nanometer, right? Uh, when they say magnification factor, the magnification is so the mask can have the larger feature size and the device will have the smaller feature size. So that's why the that is the benefit of the projection lithography, right? So yeah, okay. A lithography mask made of soda lime consists of two pitch sizes, 3 micrometer and 240 nanometer. When the deep UV compatible photoresist is exposed with an illuminating source of wavelength 248 nanometer, so they have given the wavelength of the source, both the patterns were not transferred on the resist. Uh, Mir, you said something? Second problem. Okay. Uh, So, so this is talking about projection lithography. So only in projection lithography we get such magnifications. So what happens in projection lithography is we have a mask, and after the mask we have a projection lens. Okay, and because of this projection lens, when we uh, write it on our reticle, so say this is my wafer and I am writing it here, what will happen is, so this is a big size here, right, on the mask, it will transfer to a very small area here on the, so there will be some two features here. So the projection litho setup is such that there will be a as we go from the mask to the reticle, there will be a 5x reduction in size. So they call it magnification, but it's like magnification from this side. But the mask will, we will make a so we'll usually write this mask using some direct writing step, contact based, like not contact based, something like a laser writer, direct writer. Uh, so the laser writer will have a resolution that might not be as high as the resolution that we require. So we can have a 500 nanometer uh, resolution at the laser writer stage. However, because we are using projection lithography, we are able to write very small features that are 100 nanometer. So that is the advantage of using photolithography. So in the problem what they are asking is, if the magnification factor of an optical lithography system is 5x, what is the dimension of the feature in the mask if the design feature width is 100? So the design person has given you that he wants 100 nanometer on the wafer, but now on the mask you will write 500 nanometer because it will reduce the size by 5x. Is that clear? Okay, thank you. Okay. Yeah, so in this problem they are saying that a lithography mask consists of soda lime material, and there are two pitch sizes, But when they are doing exposure with source of 248 nanometer, both the patterns were not transferred on the resist. So neither 3 micrometer pattern nor 240 nanometer pattern is transferred on the resist. Assuming the photoresist with an ideal photoresponse, identify the problem. So what might be the problem? So they are saying that the photoresist is not the problem. They are telling that it has ideal photoresponse for this wavelength. So what else can be the problem? They are also saying that both these patterns were not transferred. So it's not also about the pitch, right? So the only other information that they have given us is that the mask is made of soda lime. So now we should check if the soda lime mask is compatible with this wavelength. So turns out that that is actually the problem. The soda lime becomes transparent only after some 325 nanometer wavelength, and they are writing it at 248 nanometers. So that's why they should have used something like a quartz glass. But yeah, so that is the reason they didn't use this. So that's why they are not able to see anything on the photoresist. So basically, it's just absorbing everything that is coming. So all the light from the source is getting absorbed at the mask itself. So there will be some absorbing parts in the mask, but the top portion always has to be transparent. So this is that glass portion, right? So if this glass is not transparent, then the light won't reach the absorbing portion itself or the chrome itself. This was the chrome. So that's why we want that this has to be transparent for the wavelength given. But the soda lime glass is not transparent, so that's why this didn't work. Okay, an engineer wants to pattern a wafer using a negative resist. So they have told it is to be negative resist. For a given mask pattern shown in figure A, this is mask, okay. Select the correct type of mask to obtain the pattern shown in figure B. Okay, so first of all, what are the types of mask? So one is bright field. So here they mean only bright field or dark field, okay. Maybe I should have given options here. Yeah, so this is the pattern that we desire. So we want 4 circles on my PR film. So these 4 circles should be there, and a box has to be there, and rest of the resist has to be removed. So my resist should be present in these portions, and it is a negative resist. So what kind of mask should I use? Should I use a bright field mask or a dark field mask? So first let me tell what is a bright field mask. A bright field mask is when we are mask which has okay, wait, let me think. Yeah. Okay, so there are two possibilities, right? Either the chrome can be in my these regions. So either the chrome can be in blue regions. So those parts will be opaque, or the chrome can be in the remaining region. So either the chrome can be in the red region or in the blue region. So we'll worry about whether it's dark field or bright field later. But first, can you tell me if the chrome, so if the opaque portion should be in the blue region or the red region?
Red region.
So the chrome should be in the red region. Okay. So if it is in the red region, then this is opaque, right?
Yeah.
Yeah. If red region is opaque, then the light will pass through the blue region. Light is passing through
Yeah.
the blue region, so the photoresist will see the blue region, and it's a negative resist. So what happens in case of a negative resist?
The exposed part is insoluble.
Yeah, so exposed part will stay there. But I want the circles to stay there, right?
Right.
Yeah. So the circle should be exposed. If circles have to be exposed, then the blue region should be opaque. So blue region should have chrome in it. Chrome is the opaque portion. Is that okay?
Right.
Yeah. So turns out that okay, let me just check the answer for this. I don't know why I wrote this. Sorry, I'm always confused between bright field and dark field. So I think it's better if we check. This is the thing. Sorry. So it's dark field. Okay. So whenever we have the pattern, so whenever we have uh, chrome in the regions which are uh, boolean not of the pattern that we want to expose. So whenever we have chrome where we uh, similar to this case basically, so then it is called dark field. So so if I had chrome in the circular regions, it would be called as the bright field, and if I have chrome in everywhere except the circular regions, then it is dark field. So then in this case it should be dark field. Is that okay?
Yeah. Okay.
Okay, yeah, thanks. So, proximity effect is common in optical lithography and results in variation of critical dimension because of the adjacent feature. Select the correct statement. Proximity effect does not depend on technology and wavelength of the illumination source. So is this true or false? Hello? It's false, right? So proximity effect in fact depends on the wavelength uh, and the technology that we use. So the general trend is that if we go to lower wavelengths and if we use better technologies like stepper scanner compared to um, other technologies uh, like contact lithography or proximity lithography, then uh, then we have better like the proximity effect will be reduced. So this is an undesirable effect. It will be reduced if we go to lower wavelengths. Reduced if lambda is small, and um, uh, if we use projection litho. So it actually depends on the technology that we use. Second point is proximity effect can be corrected using sub resolution assist features. So yeah, so this is in fact true. We just saw that. Um, so the proximity effect I just showed, right, in the case of the L that we were writing, if we have some subwavelength assist features here, then that will make sure that the pattern that I get will not be a curved pattern, but the pattern that I desire. So this is actually true. And the third point is proximity can be reduced by using anti-reflection coating. Uh, so this doesn't have anything to do with the anti-reflection coating. So people do use anti-reflection coating to get smoother boundaries and to enhance the resolution, but that has nothing to do with the proximity effect. Okay, so about the source now. Okay, a lithography system with a source of wavelength lambda of 193 nanometers has a numerical aperture of 1.35. For an image contrast value greater than 2, so I want the image contrast to be greater than 2, what source shape should be chosen so that a pitch of 48 nanometer can be patterned? So my critical dimension is 48 nanometer. So the resolution, the minimum width that I can write is 48. So 48 has to be nothing but my resolution. So the so for resolution we know the formula, like W equal to lambda by Na times some K. So this K depends on the technology that we use, the source that we use, everything else, and there is a proportionality to lambda by Na. So they have given the lambda. Lambda is 193 nanometer. This is 48 nanometer. Na is 1.35. So we can determine the K, right? Do you agree? So then K comes out to be, I have done this somewhere. K comes out somewhere around 0.33. Okay. So based on that, which source should we use? So 0.33 is somewhere, 0.33 will be somewhere here. Okay. So based on that we can use either quasar source or a dipole source, because both these plots, so the quasar plot is the yellow plot, dipole plot is the green plot. So both these plots are above the image contrast that is required, that is 2. However, if you look at the conventional source, it is below, and even an annular source is below. So the blue and black curves are below the image contrast that is desired. However, quasar is above and dipole is above. So we can use these two sources uh, for the image contrast value greater than 2. Okay. In optical lithography, an objective lens with a numerical aperture of 0.5 is used to focus light on the sample. Okay. If the gap between the sample and the lens is filled with a liquid of refractive index 1.45 at 193 nanometer, estimate the improvement in resolution. Okay. So Okay, so objective lens has a numerical aperture of 0.5. Okay, so they have given Na to be 0.5, and now they have also given the wavelength as 193 nanometers. Now they are putting a liquid of refractive index 1.45, and because of this liquid we have to estimate the improvement in resolution. Okay, so again we know that resolution is directly proportional to lambda over Na, right? So from this, can you find it out? So by putting an n, we are essentially changing the Na. Na is nothing but n sine theta. So uh, W new upon W old will be nothing but right, if everything else remains the same. So this will be nothing but 0.69. Okay, so my new resolution, or the new critical dimension that I can write, is 0.69 times the old. So I have so earlier I could write, say, 1 micron. Now I will be able to write 0.69 micron also. So earlier if I go below 1 micron, it won't be focused properly, but now if I go to 0.69 micron also, it will be focused properly. So then what is the enhancement in improvement in resolution that I have got? So the improvement in resolution is nothing but this difference, right? So this was the original one, this is the new one. So this difference is nothing but 0.31. So 0.31 is the improvement in resolution that I am getting. So in percentage it is 31%. Is it okay?
Can you explain how you got n old value 1?
Huh. So okay. So it's not explicitly mentioned here, but whenever it's not mentioned, it's assumed that in the projection setup there is only air in between the projection lens and the substrate. Focus light on the sample. If the gap between the sample and lens is filled with the refracted image, estimate the improvement. So they are asking the improvement in resolution, right? So it is assumed that initially it was all air, so n is equal to 1. So n old is 1, and when they fill it with a refractive index 1.45, so n new will become 1.45. It's just that, like, whenever they don't mention it is 1, we just assume that it is air.
Okay, and how you got 0.31?
Okay, huh. So so that is like improvement in resolution they are asking, right? So the old critical dimension So the ratio of the critical dimension changes by 0.69, that is 6. So if my so initially if I could write a critical dimension of 1 micrometer on my sample, uh, so now because of adding a liquid of refractive index 1.45, I can go down below to 0.69 micrometers. So I can write now 0.69 micrometer features. So the improvement is nothing but 0.31. So I went down by 0.31.
You mean 1 minus 0.69?
Yes, 1 minus 0.69.
Okay. Okay.
That's okay, right?
Yeah, right.
Okay. Fixed beam moving stage is a patterning technique used in electron beam lithography. Which of the following statements is false? So now we are moving to e-beam lithography. So in the recap, I didn't mention anything about e-beam. So e-beam is basically just that. So there is only so much that we can do by reducing the wavelength of optical in optical lithography. So after a point, the technology becomes very difficult when we are going to reduce the wavelength even further. So people do have deep UV based lithography where they go to almost like X-ray wavelengths. However, the setup used in those cases is very complicated and it becomes very costly. So another method for going to lower wavelengths is electron beam lithography. So the wavelengths that electrons can go to is very low compared to optical wavelengths, and so that was the motivation behind e-beam lithography. So so in e-beam lithography there is a so what usually happens is people write in the area mode. So in area mode what happens, um so uh, the they scan it, so it's a direct writing method, right? So e-beam is a direct writing method. So if this is my mask, the direct writer will start to write first this column, then it will move to the next column, the next box, then the next box, like that. So it will write one area at a time and then move to the, so it can do a raster scan or a vector scan. So all these things were taught in the class. So basically it will scan through the entire mask, and wherever it is necessary to expose this, the electron beam resist, it will expose in those areas. So this is the area mode. So it will expose one area at a time. So because of that, what happens is, um, so it will essentially expose this right field first, then it will move to the next right field, then to the next, and then by the time it comes to this right field which is below, there might be some misalignment between this right field and this right field. Also sometimes in the adjacent right fields also there might be some misalignment. So because of this misalignment, say I had some pattern here like this, and now there is uh, suddenly a shift. So say I wanted something to be continuous, now there will be something like this because of the alignment error. So that is called stitching error. So in order to avoid this stitching error, people have come up with a technique called FBMS. So it is fixed beam moving stage. So in this what happens is the beam remains constant. So instead of jumping the beam over different areas, the beam stays at the same point. It might not even expose the entire area. So it will just expose a thin portion here, and then the stage will move. So it's like you have a pen and then you move the paper to write on that paper. Um, so if I want to write something like this, so I will just keep my pen here and then move the underlying substrate, or I will just keep my electron beam here and then move the underlying substrate so that I can get this pattern. So this is called as fixed beam moving stage patterning technique. So this is used in electron beam lithography. Which of the following statements is false? FBMS patterning is done by moving the stage. So this is in fact true. FBMS is only dedicated for patterning nanoscale features. Uh,
False.
False, right. FBMS offers stitch error free patterning of millimeter long features.
True.
True, correct. Okay. So last problem. Different lithography technologies and its key terms are listed in the table below. Map the technique to its relevant features. So yeah. So FVMS is just like we discussed just now. It is a millimeter scale feature, because like we are, since we are moving the stage, we can't really move it with nanometer precision. We usually write millimeter scale lines with FVMS. Extreme UV lithography. Uh, in extreme UV lithography, just like I said, so in extreme UV we go to so this is very low wavelength. So in low wavelength, the optics becomes very complicated for doing the projection lithography. So instead of having lenses, what they have is they have something called as reflective mirrors. So there will be a source of extreme UV light, and then they will reflect it by using multiple uh, uh, reflective mask, sorry, reflecting mirrors, and then the say this is the mirror, this is the mirror, and then it will land on the mask. Say my mask is here. Even this mask will also be reflecting. So then it will reflect from the mask and then come to my substrate. So this is done in deep deep UV or extreme UV lithography, primarily because it is very difficult to make lenses for such low wavelengths. So yeah, so this is D. Then nano imprint lithography. So UV nano imprint lithography. Nano imprint is nothing but we have some mask. Okay, so this is my mask, and then I put this mask directly on top of my PR, and then I press it into my PR. So if this was my PR, now I have put mask into inside my PR. So this is PR, this is mask. So the blue part is my PR, the red part is mask. So I just press the mask onto my PR so that the PR gets removed from the regions where there is pressure from the mask, and it is there in the regions where there is where the material on the mask is removed. So that's how we transfer the pattern. Uh, and then what happens is, then we in UV nano imprint lithography, we will illuminate this with UV light. So when we are illuminating with UV light, what happens is this PR becomes fixed here. So now when we remove the mask also, the PR will stay there. So so now so for the UV light to penetrate through this glass, so or this mold, so then the mold has to be transparent. So that's why UV nano imprint lithography, one of its features is a transparent mold. And the last thing is charging effects. So these effects are seen in electron beam lithography. In e-beam lithography, since we are bombarding electrons on top of our substrate, uh, if my substrate is not conducting, so there is nowhere the charges can go through, right? So the charge will stay here. That effect is called as charging. So because of this charging, there will be accumulated charges on the substrate, and to reduce this effect, we simply coat it with a very thin conductive polymer. So charging effects are reduced by using a conductive polymer. So that's all I had for today. Um, So, do you have any doubts? Did you find this session useful, or anything you want me to change about it? Okay, if not, we can close the session for today, and see you in the next week.